Hey everyone, today I want to take a look at an optimization problem that you might come across in a Calculus AB course or other similar course to that. So let's look at this example. It says, a lifeguard is in charge of roping off a safe swimming area for the patrons at the lake. He has 120 feet of rope to mark off a rectangular swimming area bounded by rope on 3 sides and the beach on the 4th side. What are the dimensions of the largest swimming area he can create? And then what is the largest area? Okay, so the first thing we want to do here is kind of get a picture of what's going on. So he's going to rope off this rectangular area here, and then on this 4th side we have the beach. Alright, so I'm going to call this side here, let's call it X, we'll call this one Y, which means obviously this side would also be X. So in this case, he has 120 feet of rope. Well, that rope is this part here. It's the X, the Y, and the other X there. So what I know is then the 2 X's plus the Y is going to equal 120 feet of rope. Then what we're also trying to maximize here is we want to dimension the largest swimming area that he can create. Well, area of a rectangle is the length times the width, or in this case, X times Y. Alright, since we're looking to maximize the area, what we want to do here is get it down so that it's down to a single variable. And we're going to do that by rearranging this perimeter equation we created, the 2x plus y equals 120. So I'm going to go ahead and solve that for y by subtracting off the 2x from both sides. And we'll get y equals 120 minus 2x. Then to optimize this, we're going to take that y and put it in for y in my equation for area here. So area equals x times 120 minus 2x. Okay, we're going to simplify that down a little bit. So the area equals 120x minus 2x squared. Now for optimization, once you have this equation, you want to take the derivative. So I write a prime here, the derivative of that is 120 minus 4x in this case. And the last step we want to do is we set the derivative equal to 0. And the reason why we set the derivative equal to 0 here is actually from an understanding of what the derivative actually is. So actually, let's go back to this step here with the 120x minus 2x squared. This is going to be some kind of parabola shape. It will look something like this, going off in both directions. And what the derivative does is the derivative gives us the slope of the line tangent to the curve. So if we say that the derivative is 0 in that case, what we're really saying here is we want to know when the slope is 0. And if we have a parabola shape like this, the slope of the line tangent to the curve is 0 when it's at the maximum value here. So that's the max value, and you can see for this line, the slope of that is 0. That's why we set the derivative equal to 0. We want the slope of the line tangent to the curve to be 0. Anyway, now let's finish out solving this problem here. So we have 120 equals 4x. I bring the 4x to the other side, adding 4x. And then we divide by 4, and we'll get that x is 30 in this case. So we're going to take that x is 30 there, and we can go ahead and substitute it back into this equation. So the y equals 120 minus 2x. I'll just put that in here. So y is 120 minus 2 times 30, or 120 minus 60, which is 60. So the dimensions are 30 feet by 60 feet. So those are the dimensions, 30 feet by 60 feet. And then the second part of the question wanted us to know what is the largest area. Well, area we said before was just x times y. So the area we just have to do 30 times 60, or the area would be 1,800 square feet. Okay, so that's how you did optimization. Hopefully that helps you out. And if you have any questions, feel free to comment below, or you could send an email directly to us at beyondthetest@gmail.com. I'd be happy to answer any questions. All right, have a good one. Bye.